Thank you.
I thought we'd start off with yet another thought experiment. We'll go through it very slowly and see if it gives you a little bit more of a comfort level with time dilation, length contraction. Again, it's on the one hand, it goes against all of our intuition. But sometimes if you do science, you have to form a new intuition, a parallel intuition. So let's try it. Let's see. Looks like this popped back on. Okay. I'm going to go through this slow, and then as promised, we'll get to E equals mc squared, and then we'll have fireworks will go off and all that good stuff. There we go. Okay, so what I've done here is I've created a reference frame for us. I'm going to call this reference frame X. But we can also imagine this as a big space station, and we're looking down on the roof of the space station. And so, okay, oh. Does that bother you that just happens? Part of the course. We'll just go with it. Okay. So as we go forward, I'm going to introduce one and then a second additional space station. And we can think of all three space stations as reference frames. So when I say X or A or B, I'm referring to the space station and the reference frame simultaneously. So that's their equivalent. And sometimes I will say, I'll use X or A or B in a different context where I'm talking about an observer in X or an observer in X. So just to make it easier to describe what's going on. That's what we're going to do. Okay. So imagine that's the roof of the space station, roof of X. But right on top of that roof, there's this laser, and it shoots a red laser beam this direction. And attached to the laser is a digital clock. And we're only concerned about one dimension right now, the X dimension. And so we've stationed the laser at X naught. That's just some arbitrary position. You can call it 0 or X naught, whatever. The laser is going to stay right here, not going to move within this reference frame. And the beam that it's shining is aligned with X naught. Now, here's our second reference frame, A, and it's traveling to our right at 0.6. Remember that 0.6 means 0.6, the speed of light, 0.6 c, and c is 1. And it's got a digital clock. And according to A, the length of this space station is 50 light seconds. And remember, the notation I use is L of A in A. Well, if it's traveling at 0.6, remember gamma? We use 0.6 because it gives us a nice gamma, 1.25. And we want to know the length of A, or L of A, in X. In reference frame X, there's length contraction. It comes out to be 40. And because 40 times 1.25 gives us 50. So anybody measuring the length of this, any X observer would say, oh, it's actually 40 light seconds in X's frame. Okay. Now, okay. A has a purple laser right here at the front. And it's got a sensor back here attached to this digital clock. And what happens is, let me go back. What happens is this laser has a sensor on it, sticking just out the front of A. And when a red laser beam strikes it, then it shoots its purple laser beam towards the back of A. And let's call the back of A naught. Well, that's A naught. And so here we are. this is event number one. Event number one is when this red laser hits this sensor, triggering the purple laser beam to go back to A naught. That's pretty scary. All right. So when the purple laser beam hits the sensor here, this digital clock's been programmed to start at 50. Why? Because it's taken 50 seconds from the time event one to get back here. So it's just going to start at 50. And the question then is, what does the digital clock show when A naught arrives at X naught? And that's event 2. Everything you want to know, everything you do in special relativity, first thing to do is to define an event. And usually that means when a location on one reference frame meets up with a location on the other frame, and that's when they can agree on things. Now they're not going to agree on their clocks, as you'll see, but the point is they agree that we are in the same spot at the same moment in time. So that's something they can agree with. But their clocks are going to be different, and let's figure out why. Let's see. So to figure out what A naught clock is, or what A clock is, we sort of have to turn things around and simply ask, what if we imagine that X naught has been traveling to the left at 0.6? That's also something they always agree on, the relative velocity. So from A's point of view, he could think, well, X naught's been traveling towards me to the, at 0.6, and X naught has traveled 50 light seconds. So per A, T times 0.6 should equal 50 light seconds. So T equals 83.33. And there we have it. Everybody comfortable with that? If you go back in time, from A's point of view, or A naught, he could think of at the moment the purple laser starts going backwards, X naught is traveling towards A naught at 0.6. And so X naught has to go 50 light seconds. And that's going to take X naught 83.33 seconds at that speed. So this says X 83.33.
Wait, why isn't it 100?
Okay, let's go back. So at some point, it registers 50, but we don't want to try to figure out, well, where exactly is it? That gets confusing, and we don't want to ask, what's this clock say? Because it depends on who you ask. This is where it gets really mind-bending. Just to go back, when this clock says 50, we could ask, well, what does that clock say? Well, it depends on who you ask, because very confusing, but an observer at X will say, well, the clock showed this, and an observer of A will say it actually showed something different. You almost have to accept that. And you kind of go, well, so that depends. But again, what can we agree on? Well, if X naught, again, I just simply say, if X naught's been traveling at 0.6, this direction. So now we put this, there's a frequent phrase you hear in relativity called the rest frame. On the one hand, that's misleading because, again, which frame is at rest depends on your opinion, on your point of view. But you can call one frame the rest frame, and then you can turn around and later look at it as the other frame is the rest frame. So what I'm suggesting is if we think of A as the rest frame, the only thing that's going on is x naught's traveling from here to here. And in the rest frame, it's 50 light seconds, and it's traveling at 0.6. 0.6 times t has to equal 50 light seconds, so it's 83.33. Again, as I'm preparing these talks, I just have this urge to apologize and how hard this is.
Yeah.
And I think I said at the beginning, I've had to go back and look at this over and over again. But I was compelled to do so because the first time I heard it, it was just so strange that you almost want to say, this can't be right. And then you go back and look at it again. Oh, okay. If you look at it from Einstein's point of view and c is the same speed in every reference frame, these conclusions have to be true, even though it goes against every intuition we have. That's what I mean by we have our natural intuition. Einstein developed a different intuition. It's hard to go back and forth from one to the other, but if you accept his premises and follow the logic, these things do work out. And that's what I've been trying to show. So anyway, at event 2, this is event 2. When they line up, this clock says 83.33. What have I done here? Let's go back. Okay. So per A, is that what I mean? 6. Oh, I know. This is getting to your point. There's another way to get to 8 point. That's right. Okay. So what I did was I said, are we sure this is right? Let's look at it a little different way. I tried to make the case that this should say 83.33. Now, the other way to look at it, or a different way, is to say, okay, remember those first 50 seconds? A naught was traveling during those 50 seconds. How far did it travel? 0.6 times 50 was 30 light seconds. So A naught started over here, and by the time the purple light hit the sensor, well, it traveled another 30 light seconds, which meant it had 20 light seconds left to get to x naught. 0.6 times t should equal 20 light seconds. Well, in that case, t would be 33.33. Add that to the 50, and you get the 83.33. Again, confusing, but it works. You almost may not be convinced that this should work. It does, and that's all I can say. Okay, now we ask the question, what would x naught say? That's very simple. X naught says 66.66. Why? Because per x, it's very simple. Remember, the distance traveled according to x is 40 light seconds. Because from here to here, according to x, is only 40 light seconds. Well, at 0.6 times t has to be such that 0.6 times t equals 40. T will be 66.66. Okay. So everything checks out. Time dilation. Right. So this is proper time. One way to check that is simply to say, well, proper time is always the shortest duration. This is clearly shorter than this. The other way to say that this is proper time is according to x is stayed stationary in its reference frame while A naught's been traveling through it. The clock that's been traveling through X is the one that does not keep proper time. But this one's been stationary in X, so that's proper time. Well, if that's proper time, we could use gamma to figure out what this would be according to time dilation. 66.66 times 1.25 equals 83.33. And again, you can't believe that these numbers work out, but they do. Because Einstein made it so. All right. All right. Let's do it. Let's check on this one other way. I want to say that we've arranged things so that there's one more event or one more, how did I say it? Oh, something else happens at event one. So now the laser beam is shooting its light up above and down below for us. And now we've got B spaceship, and it's going this way, 0.6. So what I'm trying to say here is we've created a situation of perfect symmetry. So symmetry alone should when B naught gets to X naught, it says a make here is, let's say Einstein has a twin. Here's Einstein A and Einstein B. And Einstein A has heard about special relativity at this point. And he's concerned because he has this idea that Einstein B is going to be aging more slowly because it's in B. And B, Einstein B is concerned that A is aging more slowly. And B doesn't want to get older than A, and vice versa. But symmetry tells us that at the time of event 2, they're the same age. They've aged 83 seconds in both frames. So one more little wrinkle, and then we'll move on. Let's say we get rid of, and this is just to bring up how we add velocities too. So one more wrinkle, we're going to now ignore reference frame X and remove, sort of take away the symmetry that it's created. And we want to figure out how fast B is traveling according to A, or how fast B is traveling relative to A and vice versa. Well, if you remember the additional velocity formula, which is going to come in, be very important. They agree on their velocities, and they're both 0.6. And so you add those together, and by itself, that would be 1.2. That's not allowed because that'd be faster than the speed of light. And the correction factor is 1 plus the product of both. Well, that's 0.36. So now you've got 1.2 divided by 1.36. You get 0.88. So their relative velocities are 0.88 c. Okay, and again, we're going to take away the X reference frame. And here's what we have. So there's still that laser. In fact, you could say that B is firing a laser down this way and A is firing a laser up this way. So the net effect is the same. It triggers purple lasers firing each. Now, when you have 0.88 as the velocity, gamma goes all the way up to 2.17. And the length of B in A goes down to 23 light seconds. So if that's true, then B naught must travel, according to A, B naught must travel 23, I think it's supposed to be 23, excuse me, that's just 23. So B naught has to travel 23 light seconds to get to here, and then another 50 light seconds to get to here, and that's event 2. So it must travel a total of 73 light seconds, B naught to A naught. Well, it's traveling at 0.88, so 0.88 times the time in A has to equal 73. Well, if you divide 73 by 0.88, guess what you get? 83.33 seconds. It all works out. You choose your reference frame, you choose any reference frame you want, but you have to be careful. What are you going to test? You've got to test something that happens at the same location at the same moment. When, in this case, it was when the purple lasers got triggered. That was event 1, same location, same moment. And then when B naught gets to A naught, same location at the same moment. That's when the numbers will always match up, no matter what reference frame. So again, you can do what you wish with all this information. You can just say, okay, that's enough, special relativity, except for this last part of our talk. Or you can, go through the handouts, put it aside for a month, come back to it, and see if the second time you go through it, it starts to make a little more sense, et cetera, et cetera. I leave that up to you. But if nothing else, you can see how difficult it is to do these little thought experiments. And so, again, credit to Einstein for sticking with it, because most of us, we might have had those first 2 postulates and we would have said, I don't know, it doesn't make any sense. But he stuck with it and looked at the implications. And then I'm going to show you some proof here in a second. Let me skip that slide. But here's an actual experiment that proved that Einstein was right. I'm not sure, but let's say this was one of the first times they were able to sort of prove length contraction and time dilation actually happen in real life, because it's one of the few times where you get up to speeds that approach the speed of light. The other location, of course, where that happens is in particle accelerators. But this was sort of nature's particle accelerator. What I'm talking about is when gamma rays from the sun hit or cosmic rays, I think is the proper term. Cosmic rays hit the upper atmosphere around 10,000 meters. They create muons. A muon is a particle that has a little bit of mass, so it can't travel at the speed of light. But muons have a lot of energy, and they travel close to the speed of light when they're created in this way. They travel at 0.98 C, so very close to C. And their average lifespan is 2.2 microseconds. Then they decay into other particles. But you can detect a muon and distinguish it from these other things that create it and the things that it disintegrates into. So if you can detect a muon, you can put your sensor up here at 10,000 meters, and your sensor will tell you on average there's X number of muons passing through every moment. And they all have an average lifespan of 2.2 microseconds, which means some of them actually live longer than that. But without relativity, if we didn't have relativity, this is what we would expect would happen. They're traveling very fast, but their lifespan is very, very short. So they'd only make it down to maybe 8,000 or 9,000 meters. And you wouldn't see any down here at the surface of the Earth. But let's put in relativity. We have a gamma now that equals 5. Because this has gotten so high, our gamma is quite large. And given this gamma from our reference frames on Earth, now the average lifespan is 11 microseconds. And that means that they can travel much farther, and some of them will reach the surface of the Earth. They could detect them. So that was proof of time dilation. What does it look like from the point of view of the muon? Well, the muon still has its clock we'll say well, it is itself a clock, and it lasts for 2.2 microseconds. But from its perspective, there's tremendous length contraction. So the length that it has to travel to reach the surface of the Earth is 1/5 of 10,000, let's say. So again, when you look at it from one way, you use time dilation to figure out what's going on. If you look at it from the other point of view, you use length contraction. Okay, so let's go on and we'll talk about E equals mc squared. Remember Einstein's thought experiment back when he was 16. He imagined himself going at the speed of light and looking at what a light wave looks like. And he realized that according to Maxwell's equations, it made no sense for a light wave even to exist if he's traveling at the speed of light, because in order for a light wave to exist at all, it has to be changing in time. It can't be static. Okay. Point number 2, we talked about addition of velocities before, and I just want to show you this formula. We used it a little while ago, but just to remind you, the velocity of z in B is the velocity of z in A plus the velocity of A in B divided by this denominator. And that guarantees that nothing can ever go as fast as the speed of light, if it has any mass at all. So we went through this little exercise. I made an error. I had a plus sign there last time. Now I put the equal sign in. If you remember that both are going at 0.9, their new velocity is 0.99 according to that formula. Okay, now let's, Einstein, of course, knew classical mechanics. This might look familiar to you. This is from Newton, F equals ma. Let's go a little bit farther and then we'll take a break, maybe an early break, because I know I've cluttered your head with that thought experiment. We're just doing a little review here and then we'll take a break. So force equals mass times acceleration. Let's think about ways to interpret that equation. So here's a little boy, he's water skiing, and the boat is starting to accelerate, and the boat generates a force acting through the rope on the boy. There he goes. So he's picking up speed. That's his acceleration. And he has, of course, a mass. So mass times acceleration is going to equal a force. But you can think of mass as resistance to acceleration. So another way to write this is, well, another way to think about this, what if he was much heavier, or what if there was an adult being pulled? And in this case, her mass is a little bigger, so her acceleration is going to be less. So for our purposes, this might even be a better way to think of this equation. Acceleration is the ratio of force to mass. So the bigger the mass, for a given force, the bigger the mass, the lower the acceleration. And one other bit of classical mechanics. If you apply a force over time such that the body in question goes a certain distance, the increase in kinetic energy is force times distance traveled. Just a very simple equation, but that comes from Newton. To put it another way, as you apply a force, where in this case the force is the engine, the rocket engine, as that force operates, the kinetic energy will increase and accelerate. And specifically, the kinetic energy is 1/2 mv squared. At low velocities, this is true. Okay. Let's just stop right there. We'll take a quick break, kind of clear your mind a little bit. Forget about the thought experiment for now. And this is actually easier than those thought experiments. You'll see. And so I've left you now with a little classical mechanics and see how Einstein built on those simple concepts from Newton to get to E equals mc squared. So as I say, this is all classical mechanics from the time of Newton. And we're dealing with velocities here that are familiar to us, nowhere near the speed of light. And this formula works. And the implication is, well, you know, we think of mass in day-to-day life as a constant. It doesn't change. But here was the problem. If the mass doesn't change, then Einstein argued if this keeps accelerating and you keep adding kinetic energy here, the only thing that can change is the velocity. It can go up indefinitely. And that would violate his premise that nothing can go faster than the speed of light. So he said, there's something wrong here. And he said the mistake is to assume that mass is constant. And here's what he said. He said, as you add kinetic energy to a body, maybe you increase its velocity, but maybe you also increase its inertia. Well, mass and inertia are just different words for the same thing. In fact, you can say that mass refers to two different things, actually. Mass contributes to a gravitational force if there's another mass nearby. So mass creates a gravitational field, but it also is inertia, the resistance to acceleration. And the fact that it has those two properties is not obvious, but it does. In any case, Einstein had this idea, again, thinking outside the box. What if mass increases or inertia increases as you add kinetic energy? It must get to the point of when you get close to the speed of light, you're virtually not adding to the velocity, you're just adding to the mass. As you pump more energy into this moving body, it doesn't change velocity anymore, it just increases mass. Well, according to the formulas, you can even show this graphically. So doesn't matter what you're doing to increase the kinetic energy, but if the body increases in kinetic energy, its velocity, that means its velocity is going to go up. This is, let's say, at rest in a particular reference frame. If velocity goes up linearly for quite a long time, but at a certain point, it starts to taper off and reaches this asymptote, which is c. That's its terminal velocity. It never quite reaches c. It gets close. What happens at the same time to the mass? Well, at rest, if something has mass, we call that now rest mass or m naught. Maybe you've heard of rest mass. So it's non-zero. And it remains constant for much of this process. But just as the velocity starts to taper off, it starts to increase. And it increases exponentially. So that's another way of looking at this idea that you can never get to the speed of light because the inertia becomes so immense that you can't. There's no way to. It would take an infinite amount of energy. So that's all there is to it in a way. But let's go back and work through this again as Einstein. So here's F equals ma. And remember, I think in the first lecture we talked about acceleration is just the change of velocity over time. And if you use calculus notation, you can think in terms of instantaneous change of velocity, and we call that ev et, the tiny change in velocity with a tiny change in time. Now, if mass is not constant, you can't use this equation. But we saw how mass increases as velocity increases. So we have to be precise. We have to put m inside because m is a variable that depends on velocity. Or we could say m is a function of velocity. So what we're really dealing with is the change of mv with time. And mv has another name. We call it momentum. It's usually just written as a p. So p equals mv. So we can write this. Force equals dp over dt. Okay, So now we can make, this is how Einstein went forward. So let's make an approximation. Let's say that V is very close. As an approximation, we can say that momentum is approximately mc. So we plug that in. But as we're getting close to the speed of light, we're using c. Well, c is a constant, so now we can move that outside of the differential. And now the roles have reversed. C is c, but it's the mass that's changing as we approach the speed of light. So this is just more of a more mathematical way of thinking about it. And Einstein wondered if the mass, remember there's a rest mass, and this is the new mass. It's somewhat greater than the rest mass. What's the relationship between, we call this the relativistic mass, and the rest mass? Well, remember gamma. He said, maybe, I'm not sure, I'm just imagining, he said, make a guess. Let me make a guess that gamma comes into play here again. So let's do this. Before we do that, I'll come back to that in a minute. I'll show you how it works, but my slides tell me that I went out of order here a little bit. So let's let the force act for 1 second. For 1 second. How far will the body travel in 1 second? Well, it's going close to the speed of light. So as an approximation, it would be c times 1 second. And so we can write it as force times c times 1 second on the left. And if we do that, we have to multiply the right-hand side by c times 1 second. Well, the point is this. This is distance, c times 1 second. So this is the energy that you've pumped into the body. Specifically, the change in kinetic energy. And on the right, look what we can do. We can multiply this c by this c. That's c squared. And dm by dt, that's the rate of change per unit time. If we multiply by 1 second, we find out how much the mass has changed. That would call that delta m. So close to the speed of light, we've got force times 1 light second on the left, delta m times c squared. This is the kinetic energy. And so we can say that the change in kinetic energy is the change in the mass times c squared. There you are. That's where it comes in. But he said, wait a minute, this is an approximation, and it's when we're approaching the speed of light. What if we go back to a lower velocity approximation? Oh, sorry, I went out of order again. We'll do the low velocity approximation in a minute, but here's the question. How does this v means the relativistic mass at a particular velocity? mv equals what? What function of rest mass? And again, he thought, well, maybe it's gamma. Let's just make a guess and say it's gamma. Or we can write it this way. Remember what gamma is. It's really, gamma is 1 divided by the square root of 1 minus v squared. But wait, once again, if you think about that, the units don't come out right. And I admitted that you have to divide v squared by c squared. We're using c squared is still 1, but by adding it in here, then the units come out. So we've got that. And this is another way of writing the reciprocal of 1 minus v squared over c squared is, say it's minus 1/2. The 1/2 tells you you're taking the square root, and the minus sign means you're taking the reciprocal. All right, so just take my word for it. There is a methodology in mathematics using infinite series, Taylor series approximation, binomial expansion, blah, blah, blah. A mathematician can tell you that we have a pretty good approximation of this when v is relatively low velocity. And here's what it is. You take this minus 1/2, take away the minus sign, and put it in front of v squared over c squared and change this minus sign to a plus sign. This is an approximation, but at low velocities it holds. Well, we can rewrite that as rest mass times 1, that's here. In other words, we're going to distribute, we're going to expand this expression. So it's m naught plus m naught times 1/2 times v squared over c squared. Okay, now let's multiply both sides by c squared. And we're going to put a c squared over here, multiply that mv. Multiply rest mass times c squared. And when we multiply this term times c squared, the c squared terms goes away. And here we are with our value of kinetic energy at low velocities. So again, what he's saying is at low velocities, relativistic, again, there's some velocity, it's not zero, but it's a little bit greater than m naught because it equals n relativistic mass, m sub v times c squared equals rest mass times c squared plus an additional amount given by the kinetic energy. And so we find the same thing, simplistically, we find the same thing we found at high velocity. So again, it's not a proof, but it's very suggestive to Einstein. And so he reasoned that in those intermediate velocities, this general equation still has to be true. And so then it's a matter of how do I interpret this? You might just say, well, these are just abstract variables and numbers. They don't mean anything in the real world. Well, he said, I bet they mean something in the real world. And what is it telling you? Well, this is an energy term. It's in units of energy. This is in units of energy. This is in units of energy. So it's telling us that relativistic energy equals rest energy plus the kinetic energy. Well, that's nice because energy is supposed to be conserved. So this is just a conservation of energy. So it starts to make sense. You can build a case. But you can imagine fellow scientists were not convinced. They said, well, you're using some approximations here. What does it really mean? Are we let's be skeptical about it. Anyway, that's, yeah, okay. I think I've already said all this. Yeah, total energy equals rest energy plus kinetic energy. So a year later, again, this 1905 is when he came out with all this, his miracle year. So 1906, he's thought about this some more, and he says, does the inertia of the body depend on its energy content? Actually, this says 1905, but I thought it was the following year. It doesn't matter. Anyway, he does this very elaborate thought experiment, and he writes it out in this paper. And it's hard to follow. Guess what? But in the end, he believes he's proved that E equals mc squared, period. It's just true, no matter what velocity. And it was well received by some, but others wanted to look at it. It was a hard thought experiment to follow. And they started to criticize it. They said, I think you're using circular reasoning here. You're assuming at the very beginning what you're trying to prove. You kind of stuck it in there, but there it is. You made an assumption here. That's not fair. That's not proper logic. And then others said, well, again, you're using some approximations, so it's not mathematically rigorous. By and large, to this day, this paper remains controversial. And many people don't accept it. And Einstein got that feedback. He says, all right, let me try another thought. So he did another one. And it seemed to work, but then somebody pointed out, well, this thought experiment, you didn't even use relativity. You were using an argument, kind of borrowed an argument from another previous scientist, which points out that he wasn't really the first one to suggest that E equals mc squared. There were some scientists who came before him, particularly a French scientist named Poincaré. And Poincaré used an argument that had to do with the idea that light carries some energy, but it's massless. And it can It can add momentum to particles, and so there is some equivalent between light, which has no mass but seems to have some momentum. Blah blah blah. Anyway, Einstein borrowed that argument, kind of reinterpreted it, and people pointed out. I think he gave some credit to Poincaré, but people said, "Well, that just kind of rehashed his argument. Where's relativity?" And he said, "You're right. I didn't use relativity." Apparently, he tried a couple more times throughout his lifetime and never found a thought experiment that was totally satisfactory. And yet, again, if we go to the real world, what do we find? Well, it's, the nuclear processes, nuclear decay, radioactive compounds. So if you have a parent nucleus, uranium-238, it will every so often spontaneously emit an alpha particle, and then you're left with the daughter nucleus, which is a different element, the nucleus of a different element. And when this happens, this is ejected with a high velocity, so it has a lot of kinetic energy, whereas this didn't really have any kinetic energy. And so you can do a couple things. You can measure the kinetic energy of this particle and plus the daughter nucleus. They both get a little bit of kinetic energy, and you can weigh them. I don't know how you weigh these things, but no, they know what the rest mass is of everything here. They know the rest mass of this, this, and this. And what they found is the sum of the rest masses of these two particles is less than the rest mass of this. So some mass has disappeared. A rest mass has disappeared. Where did it go? Well, it went to the energy. And so, the change in mass is the rest mass of the parent nucleus minus the mass of the two products. There's a difference there. It's a missing mass, and the missing mass happens to be the kinetic energy of the two particles. There's delta c squared. So there's your answer. I think that's a good place to stop, but I was curious. If you want to explore this more, there are more sophisticated mathematical treatments, and that I mentioned that Leonard Susskind up at Stanford did a video series, and I gave you the link to lecture 1. If you look at lecture 2 and lecture 3, it's a very, again, sophisticated mathematical analysis that came along after Einstein. And it's interesting in and of itself, again, a little hard to follow, but it's another way of showing that if you do have rigorous mathematical tools at your disposal, it's another way to mathematically show that energy equals mc squared. So I'm going to leave that. I'm not going to try to replicate that. But what I've shown you is the original evidence that suggested to Einstein that mass equals mc squared. We talked about how hard it is to do a thought experiment to prove it. We talked about a real world experiment that does prove it. And then finally, there is a rigorous mathematical process by which you can prove it without using too many approximations. Although, as I think we've talked about before, everything is an approximation. It's a matter of how close it is to ultimate truth. Anyway, I'll put together this talk today into a handout format, like I've done with the previous one. You can go back and look at it and ponder it over your coffee or whatever. But one other thing that will be in the handout, if you want to look at this, the question was: remember, Einstein kind of made a guess that relativistic mass equals gamma times rest mass. There is a way to prove that with the thought experiment, and it involves collisions and conservation of momentum. And I found the argument in Feynman's lectures. Richard Feynman, you probably know, down at Caltech, brilliant scientist. Nobel Prize winner. He was famous for giving lectures that made things clear to his Caltech students. Well, those are Caltech students, number one. That's not me. But he gave a lecture on relativity to a freshman class. Actually, he gave a whole series. He taught the freshman physics class at Caltech. And those lectures were compiled into a 3-volume book, or 3-volume work. And that was available for purchase for a long time, and now finally it's free on. Anyway, Feynman, he just had a fun way of describing these things and making complicated things sound simple. Anyway, I looked at that lecture, and he talked about how you can prove through a thought experiment that relativistic mass equals gamma times rest mass. And I tried to do a replication of his argument in a series of diagrams. So the problem is when you read source like that, they only have 1 or 2 illustrations and then a lot of words describing what's going on, and that makes it hard to follow. So I translated all those words into additional diagrams, so it's a little easier to follow step by step if you want to go through it. So that'll be in the handout too. Any questions? All right. Time to let that just percolate and decompress. And enjoy the rest of your day. Thanks for your attention. I do appreciate it.